The morning of May 8, 1945 brought an eerie silence to the forests of northern Germany. British technical intelligence officers stood in a captured Wehrmacht depot, their boots crunching on broken glass and spent shell casings, staring at the very machines that had terrorized their tank crews for 2 years. 5 Panther tanks sat motionless in the compound, their sloped armor gleaming dully in the spring light, their long 75mm guns pointing at nothing. These weren't just any Panthers. These were relatively intact specimens, mechanical predators that had earned a fearsome reputation on every front where they'd appeared. Captain James Thornton of the Royal Armored Corps wiped his brow and looked at his colleague, Major Richard Blythe. "Right then," Thornton said quietly. "Let's see what all the fuss was about." The Panther tank had haunted Allied tankers since its debut at Kursk in July 1943. Reports from the Eastern Front described a medium tank that could destroy Soviet T-34s from ranges previously thought impossible. American Sherman crews in Normandy learned the same bitter lesson. Their shells bounced off Panther armor, while German gunners picked them off at leisure. Intelligence estimates suggested the Panther combined the best aspects of German engineering: devastating firepower, excellent armor protection, and reasonable mobility. On paper, it was superior to anything the Western Allies fielded. But something didn't quite add up. British field reports told a different story, one that contradicted the Panther's fearsome reputation. Tank crews advancing through France and Belgium routinely discovered abandoned Panthers, some barely damaged, littering the roadsides. Investigation teams found these mechanical giants hadn't been knocked out by Allied fire. They'd simply stopped working. According to documentation from the British Tank Museum archives, mechanical failures plagued German armored divisions throughout the latter stages of the war, with the Panther being particularly susceptible despite its sophisticated design. The decision to conduct comprehensive tests on captured Panthers came from the highest levels of British military intelligence. Understanding enemy equipment wasn't merely academic curiosity, it was essential for planning future tank development. The War Office established a special evaluation team at the Fighting Vehicles Proving Establishment, assigning their most experienced engineers to dissect every aspect of Panther performance. These men had spent years testing British, American, and captured Soviet tanks. They understood armor metallurgy, ballistics, automotive engineering, and the brutal realities of armored warfare. Major Blythe organized the testing protocol with characteristic British thoroughness. Each of the 5 Panthers would undergo systematic evaluation, starting procedures, road trials, cross-country performance, and sustained operations under combat-simulated conditions. The engineers would monitor engine temperatures, track wear, transmission behavior, and fuel consumption. Everything would be documented, measured, and analyzed. They expected to find engineering brilliance mixed with wartime compromises, perhaps some innovative solutions worth incorporating into British designs. What they discovered instead would fundamentally change their understanding of German tank development and expose a critical flaw that had plagued the Panther throughout its service life. A flaw so serious that it rendered the tank's impressive characteristics almost meaningless in sustained operations. The first Panther roared to life on May 12, 1945. Its Maybach HL-230 engine bellowing like a caged animal. Lieutenant William Foster, a mechanical engineer from Coventry who'd spent 3 years maintaining British Crusader and Cromwell tanks, listened carefully to the engine note. Something was off. The engine ran roughly, vibrating the entire hull, and black smoke poured from the exhaust grills. Foster exchanged glances with Sergeant Thomas Whitley, a veteran automotive specialist. "That's not right," Whitley muttered, checking the temperature gauges. "She's already running hot and we haven't even engaged the transmission." The Panther represented the pinnacle of German medium tank development, a direct response to the Soviet T-34's sloped armor and excellent mobility. Weighing 45 tons, heavier than many tanks classified as heavy, the Panther featured sophisticated engineering throughout. Its Maybach engine produced 700 horsepower, theoretically sufficient for the tank's weight. The transmission was a complex piece of machinery, an AK-7200 system with 7 forward gears and 1 reverse, designed to translate that power into battlefield mobility. The interleaved road wheel suspension, a distinctive feature of German tank design, promised superior cross-country performance. But complexity carried a price. As the British engineers began their evaluation, they discovered a machine that seemed designed by brilliant theorists who'd never spent time maintaining equipment in field conditions. The engine compartment was cramped, packed with fuel lines, electrical cables, and cooling systems that left minimal clearance between components. According to technical assessments preserved in the Imperial War Museum's archives, German engineers had prioritized performance over maintainability, creating systems that worked brilliantly when new but deteriorated rapidly under operational stress. The cooling system drew particular scrutiny. The Maybach engine generated tremendous heat, and the Panther's designers had installed a sophisticated but temperamental cooling arrangement. Twin radiators sat in the engine compartment, fed by an electric cooling fan. In theory, this system could handle the engine's thermal output. In practice, the British engineers discovered multiple vulnerabilities. The radiator positioning made them susceptible to damage from debris entering through the engine deck grills. The electric fan motor frequently failed, and replacement required partially disassembling the engine compartment, a task impossible in field conditions. Captain Thornton personally inspected the fuel system, crawling into the engine compartment with a torch. What he found alarmed him. Fuel lines ran directly adjacent to hot engine components with minimal insulation. The carburetor positioning placed it near exhaust manifolds that glowed red-hot during operation. German engineers had apparently prioritized compact packaging over fire safety, creating a configuration that seemed almost designed to ignite leaked fuel. "Good God," Thornton said to Major Blythe after emerging from the compartment, his uniform soaked with sweat. "It's a bloody tinderbox. Any fuel leak and the whole thing goes up." The British team decided to proceed with road trials despite their concerns. They needed empirical data, not speculation. On May 15, 1945, they loaded the first Panther onto a transporter and moved it to a proving ground where they could conduct controlled tests. The plan was simple: run the tank through a series of increasingly demanding trials, monitoring all systems continuously. They would start with basic road movement, then progress to cross-country operations, and finally conduct sustained high-speed runs. The morning of May 16, 1945 dawned clear and cool. Ideal testing weather. The first Panther sat on the proving ground's main track, its engine idling roughly as Lieutenant Foster made final pre-trial checks. Sergeant Whitley monitored a bank of jury-rigged temperature gauges they'd installed throughout the engine compartment, recording baseline readings. Major Blythe stood nearby with a stopwatch and clipboard, ready to document every detail. "Right," he called out. "Let's begin with a simple road run. 5 miles at moderate speed, nothing fancy." Foster engaged the transmission and eased the Panther forward. The tank responded smoothly initially, its interleaved suspension absorbing the rough track surface effectively. The steering, controlled by regenerative brakes on each track, felt precise. For the first mile, the Panther performed admirably, confirming its reputation as a sophisticated fighting vehicle. Then the temperature readings began climbing. Whitley watched his gauges with growing alarm. "Engine temperature's rising fast," he reported over the intercom. "Coolant temperature is already 15 degrees above normal operating range." By the second mile, smoke began seeping from the engine deck grills. Foster noticed it first, thin wisps that quickly thickened into dark clouds. "We've got smoke," he announced, maintaining speed as instructed. The testing protocol required continuing until clear mechanical failure occurred, not just warning signs. British engineers needed to understand the Panther's failure modes, not just its capabilities. The temperature continued climbing. At 3 miles, Whitley reported coolant temperature had exceeded maximum safe limits. "She's going to blow," he warned. At 3.5 miles, flames appeared. Not dramatic explosions, but small fires that ignited where fuel had leaked onto hot metal surfaces, exactly as Captain Thornton had feared. Foster immediately shut down the engine and deployed fire extinguishers, but the flames spread quickly through the densely packed engine compartment. Within 2 minutes, the entire engine deck was ablaze. It took the proving grounds fire crew 15 minutes to completely extinguish the fire, by which time the first Panther's engine was completely destroyed. The British engineers conducted a post-fire inspection with grim determination. The autopsy revealed a cascade of failures. The cooling fan motor had indeed failed, just as they'd suspected it might. Without adequate cooling, engine temperatures soared. The extreme heat caused gaskets to fail, allowing fuel to leak from pressurized lines. That fuel ignited on contact with exhaust components and overheated engine blocks. The fire then spread rapidly through an engine compartment that lacked adequate fire suppression systems or flame-resistant materials. "It's not a design flaw," Captain Thornton concluded in his initial report. "It's a fundamental design failure. This engine installation is inherently unsafe." Major Blythe agreed but insisted they continue testing. One failure could be an outlier, the result of poor maintenance or damage sustained before capture. They needed to test multiple Panthers to establish whether this was systematic. According to records maintained by the Tank Museum, this methodical approach to captured equipment evaluation was standard British practice. One failure proved nothing, but patterns revealed truth. The second Panther received even more intensive pre-trial inspection. The engineers carefully checked every fuel line, tested the cooling system, replaced questionable gaskets, and ensured proper fluid levels. They treated this Panther as if preparing it for combat, not just testing. On May 19, 1945, they began the second trial with cautious optimism. The second Panther lasted longer than the first, nearly 6 miles before flames appeared in the engine compartment. Lieutenant Foster, now grimly familiar with the warning signs, noticed the temperature climbing earlier this time and tried varying his speed to manage engine load. It made no difference. The Maybach engine simply produced more heat than its cooling system could dissipate during sustained operation. By May 20, 1945, the British engineers had 2 burned-out Panthers and a growing understanding that they weren't dealing with isolated mechanical failures. Major Blythe assembled his team for a comprehensive review. They spread technical drawings of the Panther's engine compartment across a table in their workshop, marking failure points with red ink. The patterns were undeniable. Sergeant Whitley had compiled temperature data from both trials, and his graphs showed identical curves: normal operation for the first few miles, then rapid temperature escalation that inevitably led to component failure and fire. "The cooling system isn't inadequate," Whitley explained, pointing at his data. "It's fundamentally undersized for the engine's thermal output. Add any operational stress, acceleration, rough terrain, ambient temperature above freezing, and it cannot maintain safe temperatures." Captain Thornton had been researching German development history, reading captured technical documents and interrogating German tank mechanics taken prisoner. What he discovered explained much. The Panther had been rushed into production in late 1942, pushed by Hitler's personal demand for a medium tank superior to the T-34. Engineers at MAN, the primary contractor, had designed an excellent gun, effective armor, and sophisticated suspension, but they'd underestimated the thermal challenges of mounting a 700-horsepower engine in a compact hull. According to documentation from the Bundesarchiv cited in numerous post-war technical analyses, early Panther production models suffered catastrophic failure rates. Some units reported that only 40% of their Panthers remained operational after long road marches. German engineers had implemented numerous modifications throughout 1943 and 44, trying to address the engine fire problem. They improved gasket materials, rerouted fuel lines, enhanced fire suppression systems, and modified the cooling fan design. These changes reduced fire frequency, but never eliminated the underlying vulnerability. The fundamental problem remained. The Maybach HL-230 engine produced approximately 700 horsepower, but generated heat equivalent to a significantly larger power plant, and the Panther's compact engine compartment couldn't dissipate that heat safely during sustained operations. The British team proceeded to test the third Panther on May 23, 1945, implementing every preventive measure they could devise. They installed additional temperature monitoring, positioned fire extinguishers throughout the engine compartment, and developed an emergency shutdown protocol. Lieutenant Foster would cease operations the moment temperature readings approached critical levels, preventing catastrophic failure. This Panther was the newest of the 5 captured, a late-production AOSFG model that supposedly incorporated all the lessons learned from earlier versions. The 4th and 5th Panthers awaited testing, but the British engineers already understood what they would find. Major Blythe wrote in his preliminary assessment, "The Panther tank represents a curious paradox. Superior combat characteristics undermined by fundamental mechanical unreliability. An excellent weapon that cannot reliably reach the battlefield. Captain Thomas Henderson arrived at the proving ground on May 26, 1945, specifically to observe the 4th Panther trial. Henderson commanded a maintenance company attached to the 7th Armored Division, the famed Desert Rats, and had spent 2 years keeping British tanks operational across North Africa, Sicily, Italy, and northwestern Europe. He understood the brutal reality that separated theoretical performance from battlefield effectiveness. A tank that spent half its time undergoing repairs was worthless regardless of how impressive its gun or armor might be. Henderson walked around the 4th Panther slowly, examining it with a mechanic's practiced eye. He opened engine access panels, studied the track tension system, and inspected the interleaved road wheel arrangement. His expression grew increasingly incredulous. "Good Lord," he finally said to Major Blythe. "Who designed this monstrosity? Have they ever actually maintained a tank in the field?" Blythe smiled grimly. "That's precisely why I asked you here. I want your assessment from a maintenance perspective." The interleaved road wheel suspension drew Henderson's particular scorn. German engineers had overlapped the road wheels in 2 rows, creating a suspension system that distributed weight extremely well and provided excellent ride characteristics. But changing a damaged wheel, inevitable in combat operations, required removing multiple adjacent wheels first. In a British tank, replacing a damaged road wheel took perhaps 30 minutes. On a Panther, the same job required 4 to 6 hours and often necessitated removing track sections. "This is insane," Henderson said flatly. "In winter conditions, when these wheels pack with mud and ice, they become completely immobilized. We've seen it repeatedly. Panthers abandoned because frozen road wheels locked the entire suspension." The transmission accessibility proved equally problematic. Major repairs to British tanks' transmissions could be accomplished by removing relatively few components and accessing the transmission from outside the hull. The Panther's AK-7200 transmission required either removing the entire engine or extracting the transmission through the fighting compartment, a process that took specialized equipment and multiple days of work. Henderson detailed these observations in his notes, building a picture of a tank that required factory-level maintenance facilities for repairs that Allied tanks accomplished with basic field equipment. The engine compartment's layout particularly offended Henderson's sensibilities. "Everything is accessible," he noted, "but nothing is easily accessible. Want to replace a fuel pump? Requires partial engine disassembly. Cooling fan motor? Same thing. Simple tasks become major projects because everything's packed together with no thought for actual maintenance." According to technical assessments from the Royal Armoured Corps published after the war, maintenance burden became a critical factor in determining operational effectiveness. Sophisticated equipment that broke frequently and required extensive repairs often proved less effective than simpler systems that ran reliably. On May 28, 1945, the British team conducted the 4th Panther trial with Henderson observing. They decided to run this test differently. Rather than controlled road trials, they would attempt to replicate field maintenance, preparing the Panther as if it had just arrived at a forward repair depot. Henderson's team would service the tank using only equipment available to frontline maintenance companies: basic tools, standard lubricants, and typical replacement parts. No specialized equipment or factory-level resources. The maintenance exercise exposed the Panther's practical limitations mercilessly. Simple tasks proved time-consuming and complicated. Replacing spark plugs required removing engine cowlings held by dozens of fasteners, each requiring specific tools. Adjusting valve clearances necessitated accessing the engine from multiple angles simultaneously. Draining and replacing transmission fluid involved crawling under the tank and working by feel because visual access was impossible. After 8 hours, Henderson's team had barely completed basic service procedures that took 2 hours on comparable British tanks. "Now start her up," Henderson ordered grimly. They'd see whether this carefully maintained Panther would perform any better than its predecessors. The 4th Panther's engine caught fire on May 29, 1945, approximately 7 miles into its trial run. Lieutenant Foster had nursed it carefully, monitoring every gauge, modulating speed to minimize thermal stress, but the result remained inevitable. The fire started in the now familiar location, fuel lines adjacent to exhaust components, and spread rapidly despite immediate response from the fire crew. As flames consumed the engine compartment, Captain Henderson stood watching with his arms crossed, his expression one of vindication mixed with disgust. 4 out of 4, he said to Major Blythe. That's not coincidence. That's systemic failure. Major Blythe now faced a decision. The fifth Panther remained untested, but the pattern had been established beyond reasonable doubt. 4 trials, 4 engine fires, and extensive documentation of the specific failure mechanisms. Did they need to destroy a 5th tank to confirm what they already knew? From a scientific standpoint, 5 data points provided stronger evidence than 4. From a practical standpoint, testing the 5th Panther seemed almost wasteful. They could preserve it for other evaluation purposes, perhaps armor penetration testing or internal layout studies. The team debated the question that evening in their workshop quarters. Sergeant Whitley argued for completing the test series, emphasizing the value of comprehensive data. Captain Thornton supported preserving the 5th Panther for other studies, noting they'd already gathered sufficient evidence. Lieutenant Foster, who'd driven all 4 previous trials, offered a different perspective. "I want to test the 5th one," he said quietly. "I want to see if perhaps we've missed something, if maybe there's some operating technique that prevents these fires. The German crews must have developed methods for keeping these machines running." That comment prompted Captain Henderson to share information from his interrogations of captured German tank crews. German Panther crews had indeed developed various techniques for managing their tanks' thermal problems. They avoided sustained high-speed operations whenever possible. They conducted frequent cooling stops during road marches, allowing engines to cool before temperatures reached critical levels. They carried extensive firefighting equipment and trained specifically for engine compartment fires. Some crews jury-rigged additional cooling by leaving engine deck panels open, accepting reduced armor protection in exchange for better air circulation. "So they knew," Major Blythe said. "German tank crews understood their Panthers were fire hazards and adapted their operations accordingly." This revelation shifted the evaluation's implications. The Panther wasn't simply a flawed design that German engineers had failed to fix. It was a fundamentally compromised weapon system that required constant operational compromises to remain functional. According to post-war analysis documented in various military history publications, German armored units' operational readiness rates reflected this reality, with Panthers consistently showing higher mechanical failure rates than older, simpler designs like the Panzer IV. The British team decided to proceed with testing the 5th Panther, but with a modified protocol. Instead of controlled trials designed to test the tank to failure, they would operate it exactly as German crews reportedly did. Conservative driving, frequent cooling stops, careful thermal management. If the Panther could operate safely under these conditions, that itself would be valuable data. If it caught fire despite cautious handling, that would confirm the design's fundamental unsuitability for sustained operations. On June 2, 1945, Lieutenant Foster started the 5th Panther for what would be its final run. He drove conservatively, rarely exceeding moderate speeds, stopping every 15 minutes to let the engine cool. The Panther covered nearly 12 miles this way, substantially farther than any previous trial. Temperature readings remained elevated, but never quite reached the critical levels that had preceded earlier fires. For several hours, it appeared that careful operation might indeed keep the Panther safe. Then, a fitting failed. Not through overheating or thermal stress, but through simple vibration fatigue. A fuel line coupling loosened slightly, allowing pressurized fuel to spray onto hot engine components. The resulting fire was almost instantaneous. The flames consuming the 5th Panther illuminated more than just failing German engineering. They highlighted fundamental philosophical differences between Allied and German tank development. As Captain Thornton compiled his final technical report in early June 1945, he reflected on these contrasts. British and American tanks prioritized reliability, maintainability, and operational availability over maximum theoretical performance. German designers pursued technical excellence even when it compromised practical utility. The results spoke for themselves. 5 Panthers tested, 5 engine fires, 0 operational successes. Thornton's comprehensive report, submitted to the War Office on June 10, 1945, detailed every aspect of the Panther's mechanical failures. He documented the undersized cooling system, the fire-prone fuel line routing, the maintenance-hostile component packaging, and the complex transmission's vulnerability to failure. But his most important conclusion addressed broader implications. The Panther tank represents a cautionary example, Thornton wrote, of what occurs when design ambition exceeds engineering wisdom. The pursuit of superior armor, firepower, and mobility has produced a machine that cannot reliably deliver any of these characteristics because it cannot reliably reach the battlefield. Major Blythe's operational assessment complemented Thornton's technical analysis. He calculated that, based on their testing experience, a Panther tank company conducting a sustained road march would lose approximately 40% of its strength to mechanical breakdown before engaging the enemy. Combat operations would only accelerate attrition. A British tank battalion, by contrast, might lose 5 to 10% to mechanical issues during similar operations. This differential explained numerous battlefield observations that had previously puzzled intelligence analysts. Panthers discovered abandoned in seemingly favorable tactical positions, German counterattacks that began promisingly but faltered as mechanical failures reduced effective strength, and the Wehrmacht's increasing reliance on defensive operations that minimized movement. Captain Henderson contributed a maintenance analysis that damned the Panther even more comprehensively. He calculated that keeping a Panther battalion operational required approximately 3 times the maintenance personnel and 4 times the spare parts inventory needed for equivalent British formations. The Panther's theoretical superiority becomes meaningless, Henderson concluded, when one considers that for every Panther kept operational, the Germans must allocate resources that could keep 3 Panzer IVs running, or invest in other critical military needs. The British testing program's findings aligned with intelligence emerging from other sources. American technical intelligence teams conducting similar evaluations reached nearly identical conclusions. Soviet testing of captured Panthers, documented in post-war archives, revealed the same pattern of engine fires and mechanical failures. The convergence of independent assessments from 3 different Allied powers removed any doubt. The Panther's reliability problems were inherent to its design, not artifacts of poor maintenance or operator error. German documents captured in the final weeks of the war confirmed what Allied testing revealed. Internal Wehrmacht reports showed Panther operational readiness rates rarely exceeded 60%, even in well-supplied units. Maintenance logs recorded constant struggles with engine problems, transmission failures, and fire damage. Some German units petitioned to retain older Panzer IVs, rather than receive Panthers, preferring reliable mediocrity over unreliable sophistication. According to research published by military historians in subsequent decades, Hitler's insistence on technological superiority often undermined practical military effectiveness, with the Panther serving as a prime example. The final component of the British evaluation examined why German engineers had persisted with the flawed Panther design, rather than developing a simpler, more reliable replacement. The answer involved political pressures, industrial inertia, and institutional culture. Hitler personally favored impressive technical specifications, creating pressure for increasingly sophisticated weapons regardless of practical concerns. German armaments production was fragmented across multiple competing firms, making coordinated design changes difficult. Military leadership became invested in the Panther's reputation, reluctant to acknowledge its fundamental flaws. By mid-June 1945, the British evaluation team had completed their work. 5 Panthers tested, 5 engine compartment fires, and comprehensive documentation of systematic mechanical failures. The evidence was irrefutable. The summer of 1945 brought victory celebrations across Britain, but in quiet War Office conference rooms, engineers and military planners studied the Panther testing reports with intense interest. These documents would influence British tank development for the next decade, shaping the design philosophy that produced the Centurion, Chieftain, and subsequent armored vehicles. The lessons drawn from those 5 burning Panthers extended far beyond technical specifications. They became foundational principles for balancing combat effectiveness with operational reliability. Lieutenant Colonel James Morrison, Director of Armored Fighting Vehicle Development, convened a special symposium on July 15, 1945, bringing together the Panther evaluation team and senior designers from British tank manufacturers. Major Blythe presented their findings, concluding with a stark summary. The Panther tank possessed superior firepower and protection compared to our tanks, yet proved operationally inferior because mechanical unreliability negated its combat advantages. We must never make similar mistakes. The assembled designers discussed this mandate extensively, debating how to incorporate the lesson into ongoing development programs. The Centurion tank, then in final development stages, underwent immediate review in light of the Panther evaluation. Designers examined every aspect of the Centurion's engine installation, cooling systems, and component packaging through the lens of maintenance accessibility and fire safety. Several design elements were modified, including fuel line routing, cooling fan reliability, and engine deck access panels. According to military historians documenting post-war British tank development, the Panther's failures directly influenced dozens of specific Centurion design decisions, contributing to that tank's legendary reliability. Captain Thornton continued analyzing captured German equipment throughout 1945 and 46, eventually producing a comprehensive study titled Technical Excellence versus Operational Effectiveness: Lessons from German Tank Development. This document circulated widely within NATO military establishments, influencing American, Canadian, and European tank development programs. Thornton's central thesis, that operational reliability constituted a combat characteristic equally important as firepower and armor, became conventional wisdom in post-war tank design philosophy. The 5 burned Panthers themselves met different fates. 3 were scrapped for scrap metal in late 1945, their metallurgical components analyzed before destruction. The 4th became a permanent display at the School of Tank Technology, serving as a training aid for British tank designers and maintenance personnel. The 5th, least damaged by fire, was eventually restored to display condition and resided at the Tank Museum in Bovington, where it remains today as a reminder of the testing program and its lessons. German perspectives on the Panther's problems emerged gradually as former Wehrmacht personnel published memoirs and technical assessments in subsequent decades. Many German tank commanders acknowledged what British testing confirmed. The Panther was a magnificent weapon when it worked, but mechanical unreliability made it fundamentally unsuitable for the sustained mobile warfare Germany needed to win. Some former German engineers defended their designs, arguing that wartime resource shortages and manufacturing quality problems, rather than inherent design flaws, caused the reliability issues. Most honest assessments, however, conceded that the Panther exemplified German engineering's tendency to prioritize technical sophistication over practical effectiveness. The statistical reality told its own story. Throughout 1944 and 45, Wehrmacht Panther units consistently reported that only 50 to 60% of their tanks were operational at any given time. British tank battalions typically maintained 85 to 90% operational readiness. This differential, multiplied across dozens of units and hundreds of engagements, represented a strategic disadvantage that Germany could not overcome through superior individual tank characteristics. The British testing program, conducted on those 5 Panthers between May and June 1945, had quantified what battlefield experience suggested: reliability defeats sophistication. By the time the Panther evaluation reports were declassified in the 1970s, their lessons had become embedded in Western military thinking. Modern main battle tanks from Britain, America, and Germany itself reflected the principles validated by that testing program: balance firepower, protection, and mobility with maintainability, reliability, and operational sustainability. The Panther's legacy became a cautionary tale, taught at military academies and engineering schools as an example of how not to develop combat equipment. The 5 Panthers that caught fire during British testing in 1945 served their final purpose more effectively than they had served Germany during the war. They taught the engineers and soldiers studying them exactly what to avoid. In burning, they illuminated the path toward better design philosophy, influencing tank development for generations. The flames that consumed those engine compartments ultimately produced light rather than just heat, casting shadows that revealed fundamental truths about balancing theoretical excellence with practical effectiveness. Those lessons, purchased at the cost of 5 destroyed Panthers and months of intensive testing, proved worth far more than the tanks themselves ever had been.